We have seen the field autocorrelation trace does not tell us the real pulse shape, even the real pulse width. It cannot tell. So the correlation with delta tau simply reveals the inverse of the bandwidth 1 over delta nu. Nothing to do with the pulse width. As you have seen, the 3 cases, the pulse durations differ a lot, but they give rise to the same field autocorrelation trace. So you cannot tell the pulse width, delta t. And the real meaning of the correlation width, the width of the autocorrelation trace, is only related to the bandwidth. 所以意思是说，这个 trace 的宽度其实只告诉你频宽这个资讯而已。数学分析告诉我，这个 trace 告诉你 power spectrum。所以它当然有能力告诉你 bandwidth， 就是 power spectrum 的宽度啊。那这个宽度跟 correlation trace 的宽度大致上是反比的啊。The broader the bandwidth, the narrower the width of the autocorrelation trace. That's it. Okay. The second problem is lack of pulse asymmetry, because the field autocorrelation trace is always an even function. This is a short proof. Okay? G1 of minus tau by definition is proportional to A of t times A of t minus tau, which is t plus tau. Okay? Complex conjugate. And you can easily show this is G1 complex conjugate. Okay? So if G1 of minus tau equals G1 tau complex conjugate, it means the magnitude is an even function, but the phase is an odd function, right? Then if you look at IFA of minus tau, IFA is the field autocorrelation trace. It's equal to 1 plus G1 of minus tau absolute value times cosine of omega 0 times minus tau plus the phase of G1 with minus tau. Okay? So you have minus tau here, here, here. You have 3 places. And previously we have known the absolute value is even function. So this is G1 tau absolute value. The phase is an odd function, so this is minus phi G1, right? So you can see you have minus omega 0 tau minus phi G1, but they are within cosine argument. And the cosine is an even function. So it turns out that this is nothing but cosine of omega 0 tau plus phi G1. So it proves IFA of minus tau happens to be the same as IFA of tau. So this is a proof. Field autocorrelation trace is an even function. So even though your input pulse is asymmetric, your data trace is still symmetric. So there is no asymmetry information. 你这个脉冲的 rise edge 跟 fall edge 不一样，但是 autocorrelation trace 看不出来，你看不到任何这种对称的资讯，统统消失掉了。The third issue is it cannot measure 100% duty cycle pulse train. Okay, so I need to explain what is 100% duty cycle. In lesson 1, we have known the definition of duty cycle. Big D equals delta T over TR. Delta T is single pulse width. TR means repetition period, the pulse-to-pulse spacing. And the ratio is called the duty cycle. And what does that mean if duty cycle is almost 100%? Okay? For example, you have a pulse train like this. This is single pulse duration. This is repetition period. Okay? If your duty cycle is about like 7%. With a delay tau, you got trend number 2, represented by the dashed curve. So you can see it's possible that you can introduce a delay tau which is big enough such that trend 1 and the trend 2 are totally separated, just like this figure. Okay? And we do need total separation in field autocorrelation measurement. When your duty cycle becomes 100%, it looks like this. Trend 1, trend 2 are always overlapped. You can never create something like this. Then you can never get a full field autocorrelation trace. 就你那个 delay 怎么扫描，你就是没有办法让两个讯号完全分开。分不开的话，我的 autocorrelation trace 就是 scan 到一半停下来。那你 trace 不完整，你的 data analysis 也不会成功。Okay, so it's a problem when your post trend has 100% duty cycle. Okay. You might wonder how to measure a waveform like this. 相当不容易。
既然它完全分开，那是不是代表50% 以上就不行？
就是说真的不用 push 到100% 啊。但问题是你如果50%，它可能没有完全分开，但是重叠的部分很少的话，那 maybe 你的 trace 还 roughly 可以告诉你什么叫做 field autocorrelation function， 没有一个明确的边界。The fourth issue is we need online delay calibration because accurately resolving the fringes is essential. Okay, as our previous analysis, the field autocorrelation trace has dense fringes, and you need accurately resolve these fringes. Otherwise, your data trace can never be accurate. Okay. But do you know how dense is the fringe? 你知道这个有多密吗？ In theory, what is the fringe density? It's determined by which parameter? 两个波，我只有一个 input pulse。所以是什么东西？什么参数？这个 input pulse 的什么参数决定了这个 fringe？ Carrier frequency, right? Okay. So roughly speaking, your peak-to-peak spacing in average is 1 carrier period. So for example, if you use helium neon laser, the peak-to-peak spacing is about 2 femtoseconds. And you need at least 2 points for 1 cycle, right? So that means your delay increment at least has to be 1 femtosecond or even smaller. Okay? For each 1 femtosecond, you need to take 1 data point. And to have a clear and accurate fringe, your delay scanning has to be extremely stable and accurate. Right? Otherwise, these fringes will be of error. 所以不容易哦，这个算起来是1飞秒这个等级。那问题是一般你 scan delay 的工具是一个 mechanical stage. You can send a signal, the stage will move. Hopefully, it moves at a constant speed as you specify. But in reality, it's rarely like that. So your data, your autocorrelation trace must of certain error due to the error from the translation stage. How to solve this problem? This is one of the possible solutions you can send a reference CW laser beam into the interferometer, like the green curve. OK， 你是 CW laser， 所以它的 cycle 是固定的，跟你的 signal pulse 一起打进这个 microscope interferometer. As the output, in addition to the pulse pair, the reference CW laser beam will give you something like this, a pair of sinusoidal pattern. Okay? So not only the pulse pair interfere, but also the CW pattern interfere. So you will have, ideally, you will have a sinusoidal-like data trace due to your reference CW laser. So you can have them both. Then, whenever there is any error about the translation stage, it will be recorded in this green trace. It's no longer a purely sinusoidal function. So fringe density will change with delay. Then you know something is wrong about the scanning. And you can quantitatively correct the error by analyzing the green fringe. Then using the corrected delays, you can correct the red fringes of your data trace. So that's one of the possibilities. Any question? Or you can spend a lot of money to purchase a high-end translation stage, nanometer resolution, nanometer accuracy. You can bypass the CW reference laser. Question? Good question. 不一定。我这样画，那接下来问题是，有哪些选择可以做到这样的事？不只有一种可能。One of the possibilities is sending a reference CW laser with different frequency as your signal pulse. Like this is an infrared pulse. This is a visible reference CW laser. Then they can propagate along the same path, but detected by different detectors. One is sensitive to infrared signal pulse. The other is sensitive to your visible CW laser. Then you can have two data traces simultaneously. That is one possibility. But sometimes you might have no CW laser beam with very different central frequency or wavelengths. So the other choice is they can share almost the same central frequency, but spatially separated, like parallel with each other, but with a difference about height. OK， 不同高度打进去，那么这两道鬓是平行，但是没重合，空间上有分开，那你就有机会放两颗 detector 各自接收，仍然可以得到它。你就要冒着这个 alignment 不准的风险，万一它不是那么平行，那的确这边有的 error， 这两边承受的 error 不太一样，所以如果完全的 common path 是比较不会有这个问题 ，but 那你就要想某个方法区分，这个空间上已经完全重合了，你还有什么方法区分这两道边？用不同的 central frequency 是一个可能。那看看有没有其他可能。可以啊 ，good。所以这有点像 Lego， 对不对？乐高有很多不同的可能性，可以自己玩出来。But in our experience, without online delay calibration, the raw data trace can hardly be accurate. There are a lot of errors there. Okay, then field cross correlation. Okay. Previously, we assumed we have only one input signal, the signal pulse, to be measured. And we can only get power spectrum, which is quite limited. We have no spectral phase information. We cannot tell the pulse asymmetry. A lot of problems. How about if we have a second pulse, okay? The signal pulse and the reference pulse. Maybe we can get more information by the correlation measurement. But this time it's no longer autocorrelation, it is cross correlation because you have two components, okay? So the setup is actually quite easy. Your signal pulse comes in here, your reference pulse comes in here, and they are combined by a single beam splitter, and measure the average power as a function of delay by a slow point detector. Okay. How about the mathematical model? Okay. If you denote signal as as of t, of course, small a means temporal envelope function. Reference pulse by AR of t. Then the pulse pair, we still call it pulse pair, although the two components are different, should be, the electric field should be proportional to ES of t plus ER of t minus tau. Okay? Tau is the time delay between signal and the reference pulses. Okay. Then, using the same concept as we introduced earlier, the pulse pair's envelope function A out of t tau is proportional to AST, the envelope of signal, plus AR of t minus tau, the delayed envelope of the reference. But don't forget about the carrier term, e to the minus j omega 0 tau, as we have discussed earlier. And the slow point detector can only measure the average power. So this is the laser power, which is absolute square of envelope function. And we can not measure the envelope itself, but the time average. Okay. So everything is very similar as the analysis of field autocorrelation, except that now you have signal and the reference. You have two inputs. And you might be able to get a raw data trace like this. This time it's denoted by I sub fx of tau. F means field, x means cross. Okay, previously it's fa, a means autocorrelation, x means cross correlation. So this is cross correlation trace. How about the formula? The raw data trace is formulated as this way. I sub fx of tau is equal to, bracket means time average. P out means the envelope power of the pulse pair. Okay? And it's proportional to constant US plus constant UR plus 2 times real part of a complex function G1x times the carrier. Okay? But US UR actually means here, the average of absolute square of signal and the reference envelope functions. So it represents the pulse energies. Like US means signal pulse energy. UR means reference pulse energy. So the summation means total pulse energy, just a constant anyway. The third term matters, which is 2 times real part of a complex function, again, can be rewritten as a magnitude function times cosine function. The argument is omega 0 tau due to the carrier here, and the phi g1x tau due to the cross correlation function, the phase term of cross correlation function. And again, it's a real function because any physical quantity has to be real. Okay? And we have seen a new complex function G1x, which is defined here, AS of t times AR of t minus tau complex conjugate without normalization. Okay, so it's very similar to autocorrelation function, except that you have two different subscripts, AS, AR. Previously, just A and A star. Okay, now you have two different component functions. And this time it's a complex function with magnitude function and the phase function, respectively. And it's designated as field cross-correlation function of two complex functions, signal function, reference function. Okay. So we have something different. Now, can we get more information from cross-correlation measurement? The answer is yes, but under certain conditions. Okay? So it's possible you can completely retrieve the pulse. This is the time domain perspective. If the reference pulse is much narrower than the signal pulse, or in other words, delta TR, the pulse duration of reference, is much shorter than delta TS, the pulse duration of signal pulse. If this is true, then we can roughly write the reference pulse by a delta function. If a reference is much narrower, it looks like a delta function for the signal pulse. Okay. Then what happens? According to the definition of field cross-correlation function, G1x, it becomes AS times delta of t minus tau. Complex conjugate doesn't matter for a delta function. Okay? But with a bracket, that means time average. And you have known the product of two functions. One of them is a delta function. What is the integral? The sampling, right? The sampling at the place of the spike. Delta of t minus tau means the spike is located at t equals tau, right? So this product and the time average actually means the sampling of signal pulse at time instant tau, AS of tau. And this is a complex function again. Okay. So what is the corresponding raw data trace, IFX of tau? It's proportional to total pulse energy, a constant, plus 2 times field cross-correlation function magnitude times cosine of omega 0 tau plus phase of cross-correlation function. Okay. But if you use this relation, the magnitude of G1x is equal to the magnitude of AS, so it's here. And the phase of G1x is actually the phase of AS, is replaced here. Okay? So if you check the red part, AS absolute value times cosine of omega 0 tau plus phi s of tau. It's exactly the field of the signal pulse, E sub s of t, E sub s of tau. So it turns out that if your reference pulse is truly narrower than the signal pulse, like a delta function, your raw data trace is a constant plus 2 times the field of your signal pulse. And this is what you desire to know, right? And it's a field function. That means you not only know the envelope, but also the phase, the fringes. So this is a direct measurement. 就是说，你使用的参考脉冲，如果真的像一个 delta function， 你的原始数据已经回答所有的事情，它就是一个背景值，再加上什么你想知道的电场，就直接帮你扫描出来。OK， 那这个就是全部的嘛 ，everything is here。OK， but you have seen the requirement is pretty stringent. It is required. you need a delta-like reference pulse for this measurement. Now, what is the problem? So usually, you do not have a delta function for that purpose.